Good morning, students. Today, in these sessions, we discuss about the problems on the factor group. Show that every quotient group of an abelian group is abelian. Quotient group of an abelian group. Consider G be an abelian group. Then consider the quotient group or a factor group G by H is equal to HA such that A belongs to G. So we prove this quotient group of an abelian group is abelian. HA comma HB belongs to G by H, then HA into HB is equal to HAB, right? Because if it's a quotient, it is like this, HA into HB is equal to HAB. And A comma B, these are the elements which are taken from G. So A into B, G is an abelian, so we can write B into A. So we can write HB into HA. So therefore, HA into HB is equal to HB into HA. That is commutative law satisfies. Therefore, G by H is an abelian group. Next, show that every factor group of a cyclic group is cyclic. Let G is a cyclic group with generator A, that is, and N be a normal subgroup, N be a normal subgroup of G. We have to show that factor group G by N is a cyclic. That is, the elements of G by N are generated by the coset Na, right? The elements of G by N is generated by the coset Na. Then G by N is a cyclic, right? Let G by N is equal to Na such that A belongs to G is a factor group of G, right? We have to prove that G by N is cyclic. First, we will show this Na to the power of M is equal to Na A to the power of M is equal to Na whole to the power of M. So, case 1, if M is equal to 0, N A to the power of M is equal to N A to the power of 0, that is A power 0 is identity element, N into E is equal to N. That is Na whole to the power of M is equal to Na whole to the power of 0 is equal to, again, that is N is an identity element. So therefore Na to the power of M is equal to Na whole to the power of M. Next, if M is positive integer, Na to the power of M can be written as N into N, A into A into A, so on A to M times. So we can write as Na to Na to M times, and we can write as Na to the power of M. So Na to the power of M is equal to Na whole to the power of M. M is positive integer. If M is negative integer, consider M is equal to minus N. So therefore Na to the power of M is equal to Na to the power of minus N. N, we can write A minus 1 of N. This is N times A minus A power minus 1 into A power minus 1, so on up to A power minus N to N times. And this can be written as Na to the power of minus 1, Na to the power of minus 1, so on N A to the power of minus 1 N times. That's like a normalizer of an element A inverse whole to the power of N. And we can write A inverse into N because since normal subgroup of G, we can write Na to the power of minus 1 also to the power of N. Therefore, what we have, this is Na to the power of minus N. Minus N is M, Na to the power of M. Na to the power of M is equal to Na whole to the power of M, right? So, Na to the power of M is equal to Na whole to the power of M. It is true for all the integers. Let Ng belongs to Gn be arbitrary point for all G belongs to G. G is equal to A power M because G is a cyclic group. Therefore, we can, generator is A. Considering a generator A, G is equal to A power M for some M belongs to Z. So, Ng is equal to Na to the power of M is equal to Na whole to the power of M. So, that is nothing but every element of G by N is some power of N, Na, right? Therefore, G by N is a cyclic group. Next, if N is a normal subgroup of G and A is an element of finite order in G, then show that the element Na of the quotient group G by N is also a finite order and the order of Na divides order of A. Let G be a group and A belongs to G such that order of A is equal to is a finite order. I consider as n. N is the least positive integer such that A power n is equal to E. Right? That is the order of an element. Considering Na to the power of Na is equal to Na to the power of n. That is equal to n into, we have proved this one, n into A power n is E is equal to n. That is the identity element of G by n. Right? Therefore, Na is a finite order and order of Na is obviously less than or equal to n. Right? Next, let order of Na is equal to m and m is less than or equal to n. M is the least positive integer such that Na to the power of m is equal to m. This implies n divides m. Right? So by division algorithm, n can be written as m cube plus r. Where 0 is less than or equal to r, less than or equal to m. Now, n is equal to Na to the power of n is equal to Na to the power of n means m cube plus r. So n is equal to Na to the power of mq into Na to the power of r. We can separate this. The base is same, power is added here. So we can separate this. Na to the power of m whole to the power of q into Na to the power of r. Here Na to the power of m has n, right? Therefore n to the power of q. Na to the power of r. Na to the power of what we can write? R, because n to the power of q is E. Therefore n is equal to Na to the power of r. Next, which is contradiction that the least positive integer r is less than m. So therefore Na to the power of m is equal to n. That is r is equal to 0, n is equal to mq. So m divides n. So order of Na is divides order of A. Next, show that 1 comma minus 1 is a normal subgroup of the multiplicative group G, fourth rows of unity. Let H is equal to 1 comma minus 1 and G is equal to 1 comma minus 1 comma I comma minus 1. For all x belongs to G, xh x inverse is equal to H, right? To show this, by showing this one, H is said to be a normal subgroup. Consider for every element of G, I considering the 4 elements 1 minus 1 I minus I belongs to G, right? Considering 1 belongs to G such that 1 into H is, I considering an element 1 into 1 inverse is equal to again 1 into 1 into 1 belongs to H. Consider the minus 1 into 1 into minus 1 whole inverse is equal to minus 1 into 1 into minus 1 whole inverse means again we have minus 1, that is plus 1, it again belongs to H. Considering I belongs to G, then I into 1 into I inverse is equal to I into 1 divided by I. 1 divided by I means that is minus I. Minus I into I. I means I square minus 1, minus into minus plus. This should be what? This is a I. Right? Next. Minus I belongs to G implies minus I into 1 into minus I whole inverse is equal to minus I into 1 divided by I, right? 1 divided by minus I, and after rationalizing we have I. We get I into I is I square minus 1, minus into minus plus 1. 1 belongs to H. Next, for all x belongs to G, x into minus 1, x inverse is equal to minus 1 belongs to H. This is by considering H as the H element, only 1. Here if we considering minus 1, 1 belongs to G. 1 into minus 1, 1 inverse is equal to minus 1. Again it belongs to H. In the same way minus 1 belongs to G is equal to minus 1 into minus 1. Again minus 1 whole inverse. Minus 1 whole inverse. So what we have? Minus into minus plus 1. 1 divided by minus 1 is minus 1 belongs to H. And I belongs to G. I into minus 1 into I inverse is equal to what we have? Minus I into 1 divided by I means minus 1. Next, minus I belongs to G implies minus I into minus 1 into minus I whole inverse is equal to minus into minus plus I into 1 divided by I. Right? What we have? Minus I whole inverse means 1 divided by minus I. After rationalizing, we have I. So, I square is minus 1. Minus 1 minus plus again minus 1 into I. Minus 1. This belongs to H. Therefore, H is the normal subgroup of G. Right? X inverse is belongs to H. Therefore, H is normal subgroup of G. So, in this sessions, we discuss about the problems on factor group. Every factor group of a cyclic group is cyclic. And this N is a normal subgroup of G and A is an element of finite order G. Then we showed this Na divides order of A and every quotient group of an abelian group is abelian. Thank you.